आपकी आवाज आ नहीं रही है शायद आप म्यूट हैं
Okay, now I should be audible. So I welcome once again participant for this 4 day break. I hope we are back afresh. So it is my pleasure to again welcome and the Department of Physics and he has already given one lecture. Talking on the requirement of resolution sensing in engineering and physics, also biology. Today, expert. Sir.
Am I audible?
Yes, sir, you are audible. Please.
Okay, so good afternoon, everyone. Especially session which are post lunch. It's slightly difficult. Difficult for speaker as well as difficult for the audience. And the reason is, I am sure that many of you knows the reason for that. One of the most important reason is it's challenge. It's really challenging for both the audience and the speaker to ensure that for the speaker it is important that the audience remain active and post lunch. So I will try my best to keep you active. So since this session is will be slightly more technical, unlike the previous session, which was more generic, I will advise all of you to, if there is some questions in between, and I will also request the organizers to please let me know if there are questions in between before I proceed further. Is it fine, Professor Manoj?
Yes, sir, it is fine. And we can also have a small break.
Yeah, we will between the two sessions, we're going to have some small break. So do let me know, or where I need to stop, because these the two sessions which are one on engineering and physics related requirement for high resolution sensing, and another is more towards biochemical, biomedical, medicine, and aerospace mobility and stuff.
Yes, sir.
So please let me know where to stop. So I will accordingly I will plan.
It's up to you, sir. You can give some break as per your lecture.
Okay, fine. So let me go ahead. The today's talk is on requirement of high resolution sensing in engineering and physics. Now, one is if you see engineering and physics, we do physics and then try to address the problem of engineering. So last time I showed you this building. In another talk, you're going to see the campus. So again, let me thank all my group members and all the funding agency who have been very kind to us for providing the financial support. And many of the experiments which I will going to demonstrate you today has been done in the lab by all these research scholars. Okay, so what is the outline for today's talk? I will be talking about some basic working principle, and then we'll go to some engineering and physics applications, and then conclusion. We'll see how, as the talk progresses, you're going to see how it looks like. Since the talk is related to engineering and physics, I thought that maybe I will going to talk about what we do in NAPL. NAPL is a Nanophotonics and Plasmonics Laboratory, which is our research lab. If you look into the engineering aspect of some fundamental physics that we do, The idea is to use those physics to address some of these areas. Now, some of these areas are, the one which are above. You can talk about structural health monitoring, defense and aviation, and biochemical. Biochemical will largely go into the second part of the talk, but this particular talk will confine to these structural health monitoring and defense and aviation. These are engineering problems. Of course, you need to have a background of physics, which we'll be discussing about also, in order to address some of these aspects. So when you talk about structural health monitoring, we basically talk about strain sensors, curvature sensors, and temperature sensors. In today's talk, I am only confining to what are called as a strain sensors. And you, as we go ahead with the talk, you'll realize that these are required to monitor. These are required to monitor the health of a bridge, and also these are also required to monitor some of the aviation sectors. Further, in case of a defense, which is again engineering applications, there are work which we do in accelerometer. What is accelerometer? Accelerometers are basically the one which measure the ones which measure the acceleration. And what type of acceleration we are talking about in space? We are talking about micro g and milli g. So how to monitor this micro g and milli g acceleration? Then another part, what we'll be discussing about this flow meter or vibration sensor. These are engineering problem. We'll discuss about that. And another is microphone and hydrophone. We'll talk about some of these when we go to the next part of it. So before I plunge into these aspects, let me quickly tell you, what do you mean by high resolution sensing? Now, all of us know, if you just, if I have to tell you quickly that what is the least count of a human eye? When I'm talking about a human eye, I'm talking about spatial as well as temporal, both least count. So you see, I have written a word called spatial and temporal here. So requirements for high precision is spatial or temporal, depending upon what we want to measure. For example, if I ask you that what is the least count of a human eye? So let's talk about a spatial resolution of a human eye. Then possibly some of you may start thinking, many of you will have a 6x6 vision and stuff. No, I'm not talking about what type of vision one should have. Yeah. So what I'm talking about is spectral resolution, or I should say that what minimum our eye can detect spatially. So I hope all of you will appreciate. All of you must have seen a scale. When I'm saying a scale, I'm talking about a measuring scale, which generally kids utilize them in the class to draw lines. So if you take a measuring scale, our eye can easily, for human being, eye can easily detect 1 millimeter, right? In a gap of, our scale is around 15 centimeter. If you take 1 centimeter, within that there are 10 lines, and we can generally, unless and until you have some vision issue, a normal human eye can detect 1 millimeter easily. But if I further make that 1 millimeter further divided into, let's say, further 10, between 1 millimeter, I make 10 lines further, which is around 0.1 millimeter, or let's say 100 micron, then will our eye able to detect? And the answer is no. We can't detect that. So this is what I'm talking about. The resolution of our eye is typically around 1 millimeter. I'm talking about a spatial resolution. Let me go to the temporal resolution for that. If I talk about the temporal resolution, you will appreciate that all of you, when we see at the clock, you can see your clock. If there is a clock in your office or room or lab, wherever you are sitting, you can see a clock, and if it has a second hand, you will see that it's moving tuck tuck tuck. That means every 1 second your eye can easily detect. You can see that it's moved by 1 second. But if I ask you that within 1 second, if I further divide into, let's say 100 division is between 1 second, will your eye able to see? And the answer is no. And that is decided. That's get decided that the human eye temporal resolution is typically of order of, let's say, 0.1. Very good, will have maybe 0.1 second or something like that. So what does it mean? It means that how good one can resolve whatever we want to monitor, whatever want to detect, how one good one can resolve them, and that depends upon some of these parameters. So therefore, the requirement for a high resolution sensing is a spatial, it can be a spatial, it can be temporal, it can be a spectral. So if I ask you that, let's say, how many uh, colors are there in Vidya? All of us know that they'll say seven. But if I ask you the same question now, slightly different, that seven colors, does it mean that seven wavelengths? Loosely, you can say yes, but we know that if I consider the visible spectrum from 400 nanometer to 700 nanometer, then we have typically 300 nanometer width in lambda. And if I divide 300 by, let's say, 7 colors, so 300 by 7, if you divide quickly, you will see that it comes around 43 nanometer. That means corresponding to one color, there is a width of 43 nanometer. That means if lambda is one lambda corresponds, yes, if one lambda corresponds to one color, then there are 43 lambdas in, let's say, the Vidgyor will start from 400 to 443, and similarly 444 to 486 will be indigo, something like that. So our eye cannot distinguish all those. Our eye can broadly tell that, oh, no, this red again will have 43 nanometer. So generally, if you go to market, they say, no, oh, please give me that red which are more like a tomato, or give me red which are more like a sindoor or vermilion, or you can say that, no, give me red something like apple. So red will also have different shades, and these shades become much more evident when especially ladies goes to this cosmetic shop to get lipsticks. So you'll see that even one color will have all different type of shades. That means all those are spectrally resolved. You can still feel it is red, but then you'll see that they have different shades of red. And this is what is the resolution when we say spectral resolution. So these resolution one can see in day-to-day life easily. But when you go to quantum level, then it becomes slightly difficult. And then one has to do experiment, and then what we're going to discuss about that as we go ahead with the talk. Now the point is, in order to let's say get this high resolution sensing, we have these requirements, and these requirements can be fulfilled by one of these any techniques. It can be optical techniques, it can be electronic, it can be optoelectronics, which is hybrid, or it can be quantum. Now the whole point is, many of us knows about this electronic system, and we'll talk about that. For imaging, you go to do what is called as a SEM, or you go to do what is called as a TEM, scanning electron microscopy. So you use electron either in scanning mode or in tunneling mode, and you try to image the surface. Now these are all electronic techniques with very high resolution, and all of us use these SCM and TEM based system to resolve few nanometers. So these are what are called as an enabler, like electronics or optical. So I will try to focus on some of these, which are hybrid, optical, and some are quantum, because electronic systems are very well hitting the market. It's already in the market, and these systems are largely, if you see, has been, vastly utilized by the scientific community, unlike some of these quantum systems or optical. I hope the basic background that why high resolution sensing. I mean, what is high resolution sensing? And then what are the requirements for when we say requirements for high resolution sensing, and what are the enabler techniques that can be utilized? So if we quickly look into the high resolution sensing in engineering, so these what people are use, they do what is called as a structural health monitoring. So these are utilized to basically detect. You may be hearing in the newspaper that a lot of bridge collapsed in different part of the country, throughout the country, because in India, country like India, still we do not have a regulatory mechanism to monitor these to monitor these health of these big structures like bridges. So structural health monitoring is one of such problem in engineering, and there are a lot of techniques to do that. You may be knowing that people do what are called as a non-destructive testing by sending some sort of electromagnetic radiations. They also do what are called as a, taking some images, try to correlate the images of different part of the bridge and then try to get something from the image. They are another very standard and very good, very well-known method for monitoring the health of these bridges using optical fiber cables, which are utilized in distributed fashion to monitor different parts of the bridge. So what do these fiber cables they basically monitor? They monitor something like, if you have bridges like this, so either they monitor the compression, which can be due to at one place, or it can be elongation. In either case, if there is a compression or elongation, it's lead to the formation of some micro cracks. Then there is another bunch. Government has initiated a program called as a National Semiconductor Mission. So you know that semiconductor industry, there are a lot of it's a quite advanced industry where lithography or wafer inspection or device fabrication, all these happens. And if you see these diagram quickly, then you have in such wafer, you have some defect like 20 nanometer size defect. Now you see about this 20 nanometer, just to give you a feel, what is a nanometer? Uh, you can visualize nanometer something like, every second, your nail is every second, your nail is increasing by 1 nanometer. This is what is nanometer. So if you see your nail, you can't see with your naked eyes, but if you just do some small calculation, you'll realize that every second your nail basically get elongated by 1 nanometer. So we are talking about detecting these very precise measurement of around 20 nanometer. Or if there are some cracks or a scratch on these wafer, you can see there is a scratch in between, we can detect that. Or if two of these some sort of a ridge that is being formed, if these two get connected, or there is some sort of a defect in between, we are talking about such type of high resolution. Coming back to biomedical engineering, this is another very hot area of research. People use a lot of microfluidics to detect many of these. For early prediction or early diagnosis of many diseases, people use these microfluidics integrated with a different type of plasmonic system for detection of for detection of for detection of different type of biochemicals. Most of us know, with the advent of automation system and robotics, you need to have a very precise control and monitoring. And this is what you can see of one of a robot arm. You are trying to precisely point at some locations. And how precise are these? We are talking about some hundreds of nanometers and stuff. So these are some engineering aspect. If you look into the physics aspect of high resolution sensing, yeah, you know that quantum physics is something which is people are talking about for very precise measurement and stuff. People have been talking about this. This is what we'll also take up in this particular view graph. You can see that there is some sort of a up conversion crystal is there. These are nonlinear crystals, so you generally pump these nonlinear crystals with some lasers, and using some optical components. This is a beam splitter. You split the beam into two parts. Some part goes in this arm, some part goes in this arm, and using these two detectors, you correlate and you try to talk about some what are called as a single photon detection and stuff. So if you have to detect a single photon, if you have to identify a single photon, then you need to go into quantum physics, which tells you about what is a sensing or resolution that one can attain. Similarly, astronomy, where you use gravitational wave detection. This is a diagram which I'm trying to show you for gravitational wave detection. Many of you may be knowing about LIGO. So LIGO basically works with interferometry. So interferometry is one such area which, LIGO, all of you know, that is the most sensitive device that has ever been built by humankind. And therefore, one can infer from that if you have to make a very sensitive device, Interferometry is one of a way to do that. And therefore, in today's talk, in next, more than 1.5 hours now, from now, we'll be largely focusing on interferometric based systems for different, addressing different engineering, physics, or for that matter, in the next session, we'll be talking about, biomedical or, mobility. We'll be largely using these interferometric systems. Then in optics and photonics, of course, interferometry forms part of optics and photonics. And this is what you can see a view graph where it is showing about some near field, we say far field when D is greater than lambda. D is this distance what you are trying to monitor, and D is less than lambda. You say it is we are in a near field. So it is basically, imaging, or through objective you are trying to just image some sample. So these is again very high precision. So we are talking about lambda, which is typically few less than 1 micron. We are talking about 0.6, 0.5 micron types of value, and using that value, we precisely want to image. Then physics, if you say that then condensed matter physics is something which is you can't avoid for the obvious reason that many experiments goes into that to probe some nanoscale material. And one such technique is called as what are called as a surface plasmon or plasmonics. So this particular view diagram shows you some positive charge, some negative charge. So you can see some type of a, from positive charge, we know that the electric lines of force is going to converge at negative charge, and similarly, you can see from both. So these some coherent oscillations of these electron charges at the metal and the electric interface are called as plasmon. So these are basically some coherent oscillations. And if you take a nanoparticle-like systems, then you can see that there is again, depending upon the direction of the field, you will going to have. You can think about the electron cloud getting polarized in opposite direction as what we can see here. So all these allows you to detect, detect field which are typically comparable to that of wavelength. So these are what I am talking about, high resolution sensing where physics get into come into play. So let me quickly, yes, let me quickly go to some of the system that what we're going to talk about today is one is optical sensing system I am talking about. Now, all these whatever I'm talking about, we are basically talking about high resolution systems. So that goes without saying that we are talking about high resolution systems. If you want to make a high resolution systems using optics and photonics, or for condensed matter application, or for engineering applications, you use these parameters. One is you require a light source, then you require some sensing probe, then you require detector and conditional signal processing unit. Please note, if you look into this is a common framework for any advanced optical sensing systems. If you look into the global optical sensor market, I'm talking only about optical sensor market. Why I'm talking about optical? Because these can give you very high resolution. By virtue of utilizing a photon, which is of course massless but has momentum, this allows you to have give a very high resolution. Unlike many of the systems which are available in the market. Of course, we are not talking about SEM and TEM; those are more precise. But many of other systems you can use such optical systems for processing. If you carefully look in terms of the amount, this view graph shows you where we are using. We are using in consumer electronics, automotive and transportation, healthcare, aerospace, manufacturing, energy, and others. Please note that the 2 hours of the talk largely will going to cover many of these areas. So we'll go into more detail on that. So if you look into how this has been rising, so you see that over a period of time, it is expected that this will close to around 50 billion US dollar market by 2020, 2030. And why it is growing like anything is for these obvious applications, starting from manufacturing, infrastructure, healthcare, security, transportation, and environment. And this is where you in order to monitor them, you require a very high resolution integration system. So let me quickly tell you about optical sensing. What are the principles one utilizes for in optical sensing? Basically, you try to modulate. What you try to modulate? You try to modulate the property of a light. So what are the different properties associated with a light? It can have a phase, it can have a wavelength, intensity, and polarization. And these, one of the property get changed whenever there is some external parameter which, which interacts with the system. So as the external parameter interact with the systems, in one of these light property, you can observe the change. And then you study that change and try to detect the external parameter. As I mentioned that the key features, these are highly sensitive and therefore, therefore they can have a very high resolution also. Apart from they can be operated over broad dynamic range. Since they are photon, they do not get interfere with electromagnetic field. Uh, Using these systems, one can make a very compact system, which can be, eco-friendly and do not require many of those uh, bio waste, or I should say many of those systems which produces e-waste. So where it can be utilized, it can be utilized for all parameters, which is physical parameters, chemical parameters, or biological parameters. We'll be talking about some of them. And to use for in these parameters, basically these are some of the modulation scheme. As I already told that you need to do one of these phase, wavelength, intensity, and polarization. So you can sense one of them, and then that become the modulation parameter. Okay, so let me quickly go to some of very advanced systems, which of course is required. And these are laser electrometry. Many of you may be using them. These are required in condensed matter physics, where you have some sort of a laser source, and then followed by laser source, you have some sample which you basically which you try to scan, because these are some mapping stage, and then you have some focusing element and you have a detector. So basically changing the polarization state can give you a resolution which are mind-boggling, which are we are talking about 0.01 nanometer, which very high spatial resolution. So one of these laser electrometry, you can get very high resolution, and these are utilized for film and surface morphology. Many of you may be knowing about radar. We have what are called as a LIDAR, which is light detection and ranging. And it is amazing that the longitudinal resolution about all these, all of you are aware about radar, that how radar imaging is being done. So similarly, using LiDAR, you can get a resolution of around 30 centimeter, which is very, very difficult to get with radio waves, because those itself have a very high wavelength. But with LiDAR, we are talking about very high resolution. So these are basically utilized for surface mapping and for object detection. Another very important concept is laser Doppler vibratometry. What does it do? It basically tells you the velocity, uh, or it tells you about the structural dynamics, depending upon the light frequency. It gives you a very high resolution, uh, where you require in order to monitor the fluid flow, or you need to understand about how much is the change in frequency with respect to some vibration. So this is another area which utilizes laser, and you can get a very, very precise measurement. Of course, quantum sensing, we'll be talking more about that. These also require some sort of a laser source, and these laser source are basically where one has to create an entangled source for such type of application. Another area apart from laser based sensing is what is called as a plasmonic sensing. Please note, when we are talking about high resolution application in physics, plasmonics or condensed matter physics is something where plasmonics get utilized. So if you see, this is some sort of a glass slide you have, and on top of these glass slides, you have some metal film. And when you incident some p polarized light is the criteria to excite surface plasmon wave. So when you incident these p-polarized light on this metal and dielectric glass is a dielectric, of course, this is a coupling element here, and then you have a metal film on top of that. And of course, air is also a dielectric. So if you incident a p-polarized light on this glass, metal, and air interface, then basically what we expect that the incident p-polarized light will some part of the light will get you know some part of the light will get at some particular angle. Those angle are called as a resonance angle. At some part of the incident light will get coupled to a wave which get created at this metal and dielectric interface. I'm not saying metal and glass. I'm talking about metal and dielectric. Dielectric is your air. So some part of the incident electromagnetic p polarized wave get coupled to the metal and dielectric interface. So these waves which get created at a metal and dielectric interface are called as a surface plasmon wave. So when you incident some wave, the incident energy get coupled to these surface plasmon wave. That means the k vector of the incident wave matches with the k vector of the surface plasmon wave. So you know that the energy will get coupled to that, and the reflected light there will be less energy. And this is what you can see here in this diagram. Intensity of the reflected light at some particular value of theta is low. That means at this theta, the incident light get coupled to surface plasmon wave at the metal dielectric interface, and therefore you get lesser value of theta, lesser value of intensity at particular theta. This theta is called as a resonance angle. And if you change the dielectric constant of the adjacent medium, then you will realize that the k vector changes. We know that k equal to k0 and k equal to k0 np sine theta. So in order to match the momentum again, there will be shift in the theta. So if this shift in the theta or shift in the wavelength, depending upon what you are monitoring, either you can monitor in terms of theta or you can monitor in terms of wavelength. So any change in the refractive index of the sensing medium, which is n is changed to delta ns, there is a shift in the wavelength or shift in the theta. And you can monitor this shift to determine refractive index of the sensing medium of order of 10 to the power minus 6 RI unit. I'm talking again, I'm emphasizing it is 10 to the power minus 5, minus 6, minus 7 RI unit. So this is a very powerful technique to determine the refractive index of an unknown sample. Okay, so what people have also done is they have functionalized these metal surface with different type of target molecule and recognition of molecule, and then they try to study the field there. So basically when they try to study the field, uh, from that they can determine selectively, they can detect or they can recognize some molecule. So the selective detection of molecule is possible with such type of a system. So here you see this prism is something what you utilize as a coupling medium and stuff. The prism can also be replaced by fiber, and this is what people have used, optical fiber, which also act as a plasmonic interface for a lot of sensing application or very high resolution sensing application. Then further one can improve the resolution or make it very extremely one can make it very extremely precise by tapering some of these regions, tapering some of the regions of, let's say, an optical fiber. So if you taper some regions of optical fiber, and it is being done by what are techniques called as a flame and brush technique. So you keep the conventional optical fiber on a stage, and you pull the stage, you heat the glass. These are basically glass. So you heat the glass and then you pull the glass on both the sides. So if you heat and pull the glass on both the side, it gets tapered in the between. And you know that if you have this as a fundamental mode which get launched, then this fundamental mode, lot of field is in the outside region. These are called as evanescent field, and these evanescent field are extremely sensitive. So if any analyte or if any molecule are kept in this region, you'll realize that you can detect them. And therefore, uh, microfiber based systems become very important for very high resolution sensing systems. This one particular diagram, which I will be discussing in more detail as we go ahead, tells you about how such system can be utilized, for detection of some biomolecule. And when we are talking about these biomolecules, we are talking about some concentration like picomolar concentration of biomolecules, or in some cases nanomolar concentration of biomolecules, in some cases even femtomolar concentration of biomolecules. So this is what can be done using microfiber based systems. Then there are another type of optical fiber what people use for very high resolution system is called as a specialty fibers. So specialty fibers are basically different than the conventional fiber, because the specialty fiber you can have there's a separate class of a specialty fiber which are called as a hollow core. So you can see that this yellow region here is all hollow. There is nothing in here. It is air, and you have all around it you have some air holes which are in some regular pattern. So here the light get guided inside such type of optical fiber through band gap guidance. That means only a band of light is allowed to propagate through that. It is something like very similar to what you get in electronics, that you have such band gap structures uh, between you have band gap between valence and conduction band. Similarly, here also only a band of frequencies are allowed. So people have utilized these for a lot of applications, including considering these hollow core fiber as some nano reactor chambers. So people fill these with chemicals, do also use them with some biomolecules, and they consider these as a nano reactor or nano chambers to do all type of different interactions, and they study them for different applications. So what I'm trying to tell you is that these different type of fibers allows you to do different type of studies, whether it is chemical, biochemical, or physical parameter, depending upon what we are looking for. So as I was talking to you, that limit of detection or resolution, what you can say, is typically around some nanomolar concentration. And if you do things correctly, you can make this device very selective. We'll be talking more about this when we go to that part of the talk. Then there are a lot of work that people are trying to use for bio applications, like different type of biomolecules can be detected using what are called as a polymer optical fibers. So people have used it for some sort of detection of some sort of rare earth element like lanthanides, for different but they dope these fiber with lanthanides, and then they try to detect some biomolecules like dopamine. Similarly, you can use them. You can functionalize different type of hydrogels. What you want to depending upon what type of systems you want to monitor, you can functionalize them with hydrogels, and then you can detect them for different applications. So again, the emphasis here is that all these can be utilized for high resolution systems. So whatever I have talked with you, till now is, uh, different fiber, how it can be utilized. So one such scheme or optical scheme, what people uses or what we also uses, is based on interferometry. So what is interferometry? This is something, we know that if you have two light waves and if you superpose them properly, so there is some redistribution of energy in the systems that gives you some interference pattern. Now, you can create this interference pattern. You can create this interference pattern using some very easy, or I should say, using some very simple setup. Like you just considered a conventional single mode fiber, and then you cleave this end. You know that this is a glass, this is the air. There will be 4% Fresnel reflection. So if you incident a light, part of the light will get reflected, and then after that, you make some, you have some distance d1 for example, which is this location. So you have some reflection of a light from this interface, and then you have a mirror, which is a reflecting surface. Again, you have a reflection from this interface. So the light which is Fresnel get reflected by Fresnel reflection and the one which get reflected by a mirror. These are two I1 and I2. And since this distance is D1, or you can say D, so therefore, the light which get reflected by the mirror will have some extra phase depending upon what is this D. And therefore, the phase will be something like 4 pi n d by lambda. And then these two light will interfere to give a very nice interference pattern, something like this. Now, if you can deflect this mirror, so the mirror position from D1, it goes to D2, and this can happen. Let's say I coat a mirror with some material which through which I can deflect it. It is possible. So then this D1 will change to D2, therefore this D will change, therefore phi will change, therefore this cos will change, and therefore the condition for maxima and minima will now satisfy at a different wavelength, and therefore the interference pattern will shift, and it is this shift in interference pattern which can be utilized to detect different parameters. Now you see this D, if you take 20 micron, that means the tip of a fiber and the reflecting surface is 20 micron. You have how many dips? 1, 2, 3, 4, 5. If you increase D, then 1, 2, 3, 4, 5, 6, 7. If you further increase D, you have multiples. What I'm trying to tell you is by simply changing the D, you can change the FSR or free spectral range, that is a distance between the two dip or two interference peak or two interference dip, and you can study that for different application. That means what I mean to say that you change this cavity, this is an air cavity, between the tip of a fiber and this mirror, you form some sort of a cavity. So you change this cavity, that means the D can be changed, or you dope or you put some medium inside this cavity, and then if you put them, you can make different type of interference pattern, and then it can be utilized for some non-contact measurement, and it can be utilized for to some of these things. So this is one technique. Another is what is called as a hybrid cavity interferometer. Now this is different than the last slide, last one which we used only SMF, which is a single mode fiber. In this one, you can see that apart from a single mode fiber, we also use photonic crystal fiber, and therefore the cavity is now a hybrid cavity. The advantage of using hybrid cavity can be seen from this diagram. You can see that these are some computational results which shows that how does the field changes if you use this structure. The advantage of using these hybrid cavity, earlier you were getting these blue interference pattern. Now you see blue interference pattern or black, whatever you model interference. Now if you use a hybrid cavity, then within an interference you see you are getting another interference. So if the distance between the two peak earlier was 30 nanometer, now the distance between two peak can become 2 nanometer. This is how one can improve the resolution of an interferometer. And this is exactly what we are trying to do here. We are trying to improve the resolution of a interferometer, and then those small resolution we are trying to use them for uh, different parameter detection, which we'll be talking about. And one such is a nano displacement measurement system. So please note that since these dips, the distance between two of these peak, which is a pink one, the distance between two of these peak itself is very small. Therefore, we can track those peaks and determine the displacement. And exactly this is what we are trying to do here in this particular work. So you can see that we have some input light like this. It goes through the fiber. This is a hybrid cavity. You have this D as a movable refracting system. It gets reflected back and you get some output like this. Now, if this D, distance of the mirror, if I plot to wavelength of a shape dipped in the interferometer, I get a linear plot. That means I change D by a small number. You see that there is a change in this D by typically less than some micron we are talking about. And then we monitor the wavelength of the dip. The change, there is a 15, 23, 24. So the dip or one of these lambdas we try to track. So these lambda changes. It is important to mention here that if this D is not appropriately chosen, then you may get the distort. You may get a pattern something like this. That means You basically kill the interference pattern, which we should not do that. This is the limitation of this system, that your D cannot be for any value of D. So as long as you are in a correct value of D, then you get a very nice interference. So let's say when D was 110 micron, that is, this is D was 110 micron, you are tracking one of these interference dip, you are getting dip like this. Please note, it is 1550 to 1554. We are talking about very narrow wavelength range. So you go on reducing the value of D from 110 to 109, you see that there is a shift in the interference pattern. It has to be, because the cavity length is changing, cos phi will going to change, intensity will going to change, and maxima and minima condition will satisfy at different lambda. This is what you are getting. If you plot them carefully, then you realize that for D equal to 110 micron, you have this curve, where for D, if you go on increasing the value of D, the sensitivity decreases. That means you cannot go on increasing the value of D. Only for certain optimized value of D, you get a nice interference pattern. And those one can demonstrate, and this is what we have demonstrated, that for every 1 nanometer displacement in D, I will again repeat, that means if your object move by a distance of 1 nanometer, our systems will going to measure 32 picometer shift in the interference pattern. That means for every 1 nanometer, then this type of system can be utilized in robotics arm. If your object need to be precisely located, you can put such type of system. And if object move by 1 nanometer, you can see on your screen that there is some shift in the interference pattern by 32 picometer. So this is how it can be utilized for nano displacement sensor. Now the important point is, if I quote, this is what I was talking to you. If I have this system mirror, and I coat this mirror with some neodymium magnet, that means I take a mirror. To this mirror, I attach some sort of a diaphragm, and then on that diaphragm I attach some neodymium magnet. And if I apply a magnetic field, you know that the magnet will get attracted or repelled depending upon what type of polarity we are talking about, and accordingly the cavity length will change, and we will able to detect magnetic field. This is one way in which one can detect a magnetic field. And you can see here, this is exactly what we have tried to done here, that for different cavity we have shown you how the interference pattern will look like. And then when we plotted wavelength shift in the interference dip versus field in millitesla, so for different value of D, that means for different value of cavity, you get for 20 nanometer the cavity, you have the maximum field. So this technique does not only tell you about the magnitude of the field that is being applied. So generally we are able to monitor here some millitesla field, but it also tells you the direction of the field. So you see that the slope of these two are different. For attractive field, you have such type of slope. For repulsive field, you have a different slope. So such type of cavity interferometry allows you to do magnetometry for different type of attractive and repulsive field. Now the point is, if you put a oscillating field, then depending upon, all of us know that B equal to B0 cos omega t. So if we know omega, you know frequency. So if you incident some known field to this diaphragm, let's say 615 hertz in this case, and do the time series analysis of this, you will realize that you have some oscillating field like this. Now the important point is, this oscillating field can be utilized for the characterization of frequency of the oscillating magnetic field. And this is what exactly we have done. So this is omega equal to 200, 400, 615 and stuff. And please note that using such type of configuration, one can detect what is called as a dynamic magnetic field. That means you can monitor the dynamic magnetic field, not only a static field, but also the dynamic field, which are time varying magnetic fields. So such type of systems can be utilized for magnetometry. further addressing the engineering problem, one can also do what are called a hydrophone, which are utilized to map underwater. So, systems configuration is something similar to the last part. Of course, here we are using a aluminum mirror, not a magnetic material. We are using some aluminum mirror. And this particular view graph, why I'm interested to show is as follows. So you see, this is a company which is a very reputed company globally, B&K Hydrophone, Bruel and Kaiser Hydrophone, which is a very reputed company in this hydrophone business. And this is our developed hydrophone, which are at IIT Bhubaneswar we have developed. This is optical hydrophone. And you see what it is showing is this is some sound of a dolphin. So when dolphin, make a sound in water, so they try to communicate with one another. And if you do the response, if you do the frequency response of that sound, it will look something like this. So it can be generated in MATLAB. One can generate them. So please note that these are same. Please, it is also important to note that this system is coming with what is called as a signal conditioning system. So this system has what is called as a signal conditioner. That means it basically, if this oval shape is my signal, so this is a noise floor. So basically, it do the processing of the signal to give you such type of a spectra. In this case, you see the noise floor is much smaller. You have a signal which is more dominant. An important point is these are raw data. We have not done any signal processing here. These are raw data, and therefore these raw data it's more precise without signal conditioning than what is commercially. This is your available, this is your commercial hydrophone. This is what we have developed in our lab, this system. Again, we are talking about high resolution. We are talking about something like 8.94 sort of nanometer per millipascal at this particular frequency. And if you talk about some type of a what is a detectable pressure that one can heard is something around 0.3 micropascal per under root. These are unit in which you represent the minimum detection pressure. Of course, these have certain advantages also. Another important work for engineering aspect is industrial fluid measurement. So if you look into the literature, people measure the velocity of a fluid using this value, which is ST is your Strouhal number, F is your vortex heading frequency or some sort of a frequency. D is the diameter of the cylinder, or you can say diameter of the pipe under consideration, because fluid, if suppose that fluid is flowing through some type of a pipe, and V is your mean velocity. So it gets through these relations. This is, market, you have some piezo sensor, and you don't have to worry much about that. What I'm trying to tell you here is as follows. If you use two type of interferometer like this here, the advantage what you get, you don't have to worry much about these. These are some interference pattern which we have discussed about. You try to focus on this particular plot. The red one is single probe data. That means you have only P1 or P2, and the distance between them is 6 millimeter. So these are two probe. P1 is probe 1, P2 is probe 2, and this is your fluid which is going on. The red arrow is a fluid, and this is some bluff body which create these vortices frequency. I will show you as we go ahead with the talk. When we are talking about high resolution sensing, this is what you have to focus on. The single probe data is this red one. You see this red one, and the combined probe data is the blue one. You can clearly make out that red one is more noisy as compared to the blue one, right? So this noise can be suppressed if we use some type of two probe systems, and this is what is the USP of this work which we have tried to show. We also showed that such type of systems are temperature independent. That means if the fluid temperature can go around 250-100 degrees centigrade also, then these remain largely flat. these remain largely flat. And one can control the SNR, which I have told you here, that signal to noise ratio can be controlled. So the type of flow meter that what we have developed, it can operate at 250 degrees centigrade. It has 1:80 degree, 1:80 turn down ratio. That means it is able to have it has a very broad frequency range. What does it mean? It means that if you recall the last slide where a Stroll number was related to frequency, it can detect a small frequency as well as very large frequency, which can be in a ratio of, let's say, if one frequency is 100, another can be 8,000, or this is what it means. If one is 100, then 100 times 80 is 8,000. So it can detect 100 hertz also, it can detect 8,000 hertz also. This is what I mean. And these are extremely accurate. So when I say extremely accurate, what I am talking about that such type of optical systems or interferometric based systems, what the type of number it gives is not possible with the commercial level. I hope I will able to play this video. I don't know though. Can I play it? Pointer option. Are you able to see the video?
Yes, sir. Yes, sir. It is.
Okay. So you see, this is a photo detector. The system that we have developed, what I am trying to show you here is that system. You see, this is a developed flow meter. This is something similar. The important thing is these numbers, we are just trying to compare with these two. It is 2.63, this is 2.66. So such type of system, it is very, very difficult, to monitor such type of systems. If you have to, develop systems which can be more precise than what we have shown you here. So what I'm trying to mention that you can always say, sir, then what is since the system that you have developed and the systems what has been shown are both same. Yeah, are both same. So the idea is that we can go with a better systems, provided the systems that we have developed is better than what is commercially available. Therefore, we cannot compare with the commercially available system the potential of the systems that what we have developed. This is the very updated work which I thought that maybe I will share with you, which are called as a photonic integrated circuits, something like electronics integrated circuit. So what is this photonics integrated circuit is as follows. If you carefully look into this, that you can make such type of structures which can be utilized, for uh, all the different stuff which electronic circuit can does. Like you can create a bus waveguide, you can create a ring resonators, you can get output, and then you can utilize these micro resonators for different sensing application. You can make these Mach Zehnder interferometer on chip. So this is, this is a silicon, then this is SU8. So you can make such type of, this is a silicon, this is SU8. So you can make them for a lot of different applications like temperature or refractive index sensing. So these are very advanced techniques which are called as a photonic integrated circuits, which can be utilized for high resolution systems. I can see my watch. It is about 3:10. I'm yet to finish the first part of my talk. So this is, I think, will going to be the last topic covered under this. So would you like me to continue with this or go to the second part of the talk, which is more towards, which is more towards bio, or you want to confine to this single photon, which is more towards quantum, and we're going to discuss something about that. But I'm fine with either way.
Okay, sir. So maybe we can take the questions this session and then take a break, and then
Okay.
we can
Okay.
cover maybe both the aspect or maybe then
Yeah, so let me take, if there are some questions, maybe that can be asked.
Or maybe we can give some time to the participant to post the questions and you can address the queries after the break.
After the talk?
After the break.
After the break.
Before
So we can go for a break now?
Yes, maybe and repeat after 5 minutes.
Okay.
So
I am available. I am available.
okay.
So
Meanwhile, participants are advised to post their queries straight away.
pardon?
Meanwhile, I am asking for the participants that they can post the query in the chat box.
Yes, 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 yes.
Okay, sir. So we meet again in 5 minutes.
Okay. Sure, sure, sure.